Hi everyone, today we're going to talk about topic 3.6, deviations from the ideal gas law. So in reality, a lot of gases can behave ideally, but in most cases gases don't really behave ideally, right? And so KMT makes assumptions that aren't always true. The biggest assumptions is that KMT only works at high temperature and low pressure. Right, at low temperatures or really high pressures, KMT doesn't really model the behavior of gas that accurately. And so if we look over to our right, we have two different graphs, one showing PV over nRT at high pressure and one showing PV over nRT at low pressure. It's saying for an ideal gas, right, PV over nRT should equal 1 in both cases. If you solve that for any ideal gas, it should be 1. But in reality, at a high pressure, for hydrogen, for example, we see that PV over nRT should go up as pressure increases. And if we have something like CO2, right, that one behaves very unideally at, high pressure, but not too high. PV over nRT goes down, but then there's this point right here at maybe around, 80, where suddenly it starts jumping up. Right, and so what this is saying is that at high pressures, KMT doesn't hold true, and then gases start behaving unideally. And the same can be said for low pressure, as you see on the right. Now, of course, you're never going to be asked to kind of draw out those diagrams or predict what a diagram is going to look like, but you should understand the assumptions of KMT and when those actually break down. So the two big assumptions are negligible volume of gas molecules. Right, the molecules, not the entire gas, but the molecules themselves. At high pressure, this statement is untrue. Right, and so if you really compress the gas, like in this scenario right here, now the gas molecules themselves actually have some amount of volume that cannot be ignored. And so at really high pressures, this assumption is untrue. The other one is no IMFs, right? We said that KMT states that gases do not have IMFs. This at high temperature is untrue. So if you really increase the temperature of the gas, now there are these IMFs that are happening here. And so this would be an ideal gas at, for example, room temperature, and this would be a real gas at high temperature. Now, you're never going to have to actually solve this equation or do any calculations with this equation, but I wanted to show you that there are ways to kind of model real gases a little bit better. This is known as the van der Waals equation, and so you can see it looks a little bit like the ideal gas law. We have our P term here, we have our V term here. It's just now you've added P number of moles squared times A, which is this constant right here, which we've calculated for pretty much every gas that is commonly known, over V squared, and then for the V term, you also have the number of moles times this constant B, which helps correct that unideal behavior, and then again, that is still equal to nRT. You don't have to actually solve this, but if you have a real gas, for example, this is the equation that you would use to model that gas, not the ideal gas law. The main takeaways that you really need to remember and kind of understand is that pressure may be less than what is calculated. Because of attractive forces between gas particles and this is normally ignored in the ideal case. Right, and so this is essentially where IMFs come into play. Right, IMFs, basically, because of those IMFs, the pressure of your gas might be less than what is actually calculated, and the volume may be greater due to space taken up by hot gas particles, which again, this is ignored in the ideal case, where they assume that gas molecules do not have any volume, right? And so this is our high temperature case. And so pressure might be less because of IMS, and volume may be greater at high temperatures. That is the most important thing to remember. And I'm going to box, right, high temp, volume, IMFs, pressure. And so if you're asked to explain an unideal gas or non-ideal behavior, this is what you need to think about. We'll go over a few practice problems in class and also some more MCQ and FRQ practice. But other than that, thanks, guys.